This video connects averages and deviations to the big idea we have been building toward: how your data is actually spread out. Knowing the mean or deviation values rarely supports a solid business judgment. We will explore Chebyshev's rule, the empirical rule, and z-values as practical tools to understand distributions and to compare results fairly. The focus is interpretation, not calculations, so you can use these ideas confidently while making real decisions based on estimates obtained from your samples. In many reports, the first numbers you see are the mean and maybe the standard deviation, often presented as standard error. However, these two numbers by themselves do not tell you how values are actually distributed, just how widely they are spread. The mean gives you the central location, while the standard deviation describes how far values typically sit from that center. Chebyshev's rule and the empirical rule use those two numbers to turn spread into actionable statements. For instance, about this % of weekly sales will be in this range, or we expect next week's sales to be between this range with this percentage likelihood. Thinking this way lets you treat your data more like a probability story, even when you only have a sample. This narrative about distribution is what helps you judge risk, outliers, and what normal really means in your data. Chebyshev's rule is the general-purpose option that does not assume your data follow a normal bell-shaped curve. While sales, revenues, and costs are more likely to follow the bell-shaped distribution, customer acquisition or customer behaviors often follow other types of distribution. Mathematically, with advanced calculations, each of these distributions can be estimated in different ways. However, from a more basic perspective, just two numbers, mean and standard deviation, are sufficient to get some idea of a variable's expected behavior. This rule allows you to say that at least 75% of values of a dataset fall within two standard deviations from the mean in either direction. Similarly, at least 89% of observations fall within 3 standard deviations, and at least 95% within 4.5 standard deviations from the mean. These are minimum guarantees, not exact proportions, which is why they can be safely used for any distribution. The trade-off is that the intervals become quite wide as you try to capture more of the sample. In practice, that means Chebyshev is a conservative safety net when you do not trust or cannot assume a normal distribution. Consider the sample of 10 weekly sales, where the mean is 26.2 units and the standard deviation is 4.78 units. Using Chebyshev's rule, the interval for 2 standard deviations runs from 16.64 to 35.76, and at least 75% of weeks should fall in that band. In this small example, all 10 weeks happen to be inside that range, but the method does not depend on the sample size. You would apply it the same way to a much larger dataset. As we expand to 3 and 4.5 standard deviations, the ranges grow from 11.86 to 40.54, and then from 4.69 to 47.71 units, covering at least 89 and 95% respectively. This illustrates both the usefulness and the drawback. You gain coverage, but the practical business meaning of such wide intervals can weaken. As you push Chebyshev's rule to cover more of the data, the bands can become so broad that they stop helping you make decisions. Saying that at least 95% of weekly sales lie between roughly 5 and 48 units might be true for the sample, yet it is not very helpful when planning inventory or staffing. The width of those ranges depends heavily on the standard deviation. Larger samples can stabilize the mean and spread, making intervals more meaningful, but the trade-off between coverage and usefulness still remains. Each time you interpret such a range, ask whether that much width aligns with the level of precision your decision demands. So yes, the confidence is high with 95%, but the use value? It may remain unclear. In the standard deviation is much smaller than the mean, or the coefficient of variation is very low, this rule often proves more meaningful than we see in the illustration we have used here. As opposed to Chebyshev's rule, the empirical rule steps in when you either know or reasonably expect your data to follow a normal bell-shaped distribution. With that assumption, about 68% of observations fall within 1 standard deviation, about 96% within 2 standard deviations, and about 99.99% within 3 standard deviations from the mean. Compared to Chebyshev, these intervals are narrower yet cover more of the data, which makes them more informative when the assumption is appropriate. You still rely only on the mean and the standard deviation, but now you are describing a more specific, structured shape. The key decision is simply whether treating your variable as roughly normally distributed is reasonable for the business context. Like we mentioned earlier, costs, revenues, profits, and many other commonly used business variables often follow approximately normal distributions. However, there are quite a few variables, particularly those that are collected from customer bases or CRMs or qualitative data and surveys, that fail to meet the normal distribution criteria. Using the empirical rule willy-nilly can be misleading in the latter cases. Analysis of distribution types is beyond the scope of this certificate, but as a decision maker, as long as you are alert and ask the right questions about interpretations based on underlying data, you can avoid errors and correctly interpret the signals that often show up in reports and data dashboards. Using the same weekly sales data, the empirical rule offers a sharper picture of how sales concentrate. With a mean of 26.2 and standard deviation of 4.78, the one standard deviation band runs from 21.42 to 30.98, and around 68% of weekly sales are expected to be within this interval. In the sample, weeks with 18, 31, and 33 units lie outside that band, which is 30% of the 10 observations, reasonably close to the 32% you expect to be outside the normal band. The 2 standard deviation band is 16.64 to 35.76 and should include about 96% of weeks, while the 3 standard deviation band from 11.86 to 40.54 essentially captures all weeks at over 99% coverage. However, a claim like all weeks are between 11 and 40 units is technically accurate yet not very informative, whereas about 2/3 of weeks are between 21 and 31 units gives a focused sense of typical performance. Here's a fun fact for you. The word normal refers to that middle 68% or 2/3 of the data. Any data outside that initial range is considered above or below normal, and extreme data points are defined as the ones that fall outside the second band. So, the top 2% or the bottom 2% represents the abnormal or unexpected values. Think of it in terms of human behavior. Most normal people are the 2/3 that fall into expected behaviors. The ones that need or get the most attention are the ones in the top or bottom 2% in terms of unexpected behavior. Say that you want to compare weekly sales for 2 very similar markets because you want to launch a new product. Both markets show a mean value of 35 units, but the standard deviations differ. Market 1 has a standard deviation of 3 units, and Market 2 has a standard deviation of 5 units. Applying empirical rule yields a narrower range for Market 1 and a wider range for Market 2. If you expect your product to be a higher value product that is likely to do well, choosing Market 2 makes more sense because of the wider spread. If you are more worried about the product's performance and know that its value is similar to your existing products, then choosing Market 1 for launching gives a narrower but more reliable expected performance. Z-values translate any given data point into the number of standard deviations it sits above or below its group mean. The formula is simple. Subtract the mean from the value and divide by the standard deviation. That single unit-free number tells you how unusual or strong the performance of a single value is relative to its own group, regardless of the original scale. This is vital when groups have different spreads, since a raw value of 42 can mean something very different in a tightly clustered group than in a widely spread one. Thinking in Z-values moves you from absolute scores to relative standing, which is often what truly matters in business comparisons. Continuing with our market example from earlier, if your product research team expects it to sell at least 40 units each week based on pilot group responses, you should not rely exclusively on the empirical rule. Calculate the Z-value of 40 for each market. In Market 1, it could outperform other products with a Z-score of 1.67, whereas it falls in the first band or normal range in Market 2 with a Z-score of 1. If you need higher metrics for the new product, Market 1 is where it will really shine. In Market 2, sales of 40 are expected for your products anyway. Now say that you are trying to judge how your new product performed in 2 completely different markets. You sold 42 units in Market 1 that averages 35 with a standard deviation of 5, while you sold 43 units in Market 2 that averaged 38 with a standard deviation of 4. Your new product C value in Market 1 is 1.4, and in Market 2 it is 1.25, so product outperformed in both markets. However, product outperformed other products more strongly in Market 1. Even though the sales raw number is higher in Market 2, the product performed better in Market 1 when accounting correctly for the mean and spread. This checkpoint directly applies to other business settings where groups, customers, departments, or time periods have different baselines and variability. Bottom line, don't rush into making decisions without correctly extracting information from the data first. Effective interpretation starts by pairing the mean with the standard deviation, so you see both central performance and typical deviations. Chebyshev's rule gives conservative coverage guarantees when you cannot rely on a normal shape, while the empirical rule offers tighter, more informative bands when a bell-shaped distribution is reasonable. Z-values help you compare individuals or results across datasets with different spreads by expressing distance from the mean in standard deviation units. As you apply these tools, always balance mathematical coverage with business usefulness, avoiding intervals so wide that they stop informing decisions. Used thoughtfully, these concepts turn raw data into clearer stories about performance, risk, and relative standing. Being data-informed implies that you are not just glancing at the numbers and deciding based on what looks better in raw terms, but focusing on what performs better in business terms.